So here we have a constraint optimization problem. The problem starts out like any sort of odd constraint optimization problem. We're having a function with two arguments, x1 and x2. It's cubic in x1, so perhaps you can already imagine what the function sort of looks like. And we have a constraint. In fact, we have two constraints, and that is sort of the slightly new twist to this question. The first constraint here says that x2 should be smaller or equal to -4 plus x1, and the second constraint indicates that x1 should be smaller or equal to 2. So that doesn't actually involve x2, so it doesn't constrain anything about x2, but it constrains x1. And what we want here is the solution to this problem, but that solution has to meet both of these constraints. So before we continue and see how we will continue to apply our standard Lagrangian recipe to solve this problem, we want to have a look at what these two constraints actually mean, and that will help us to understand not only what the problem is, but also how we're going to solve it. So here we go. That was David Card. I was listening to, that was wrong, to his Nobel lecture. Can only recommend that. And go back here. This is what I want. Here we go. So here is an image of what this constraint actually means. Okay, so we are having two constraints. Let's look at the first one. x2 is smaller or equal to -4 plus x1. So what we have here is we have our x1 axis and we have our x2 axis here. And here is the origin. So this here in the middle is 0, 0. And you can see, if you in that constraint for a moment think about the equal sign only, so not smaller than equal, but just think about equal, then what this describes is just a line. x2 is equal to -4 plus 1 times x1. So here we have our intercept is here at that -0.4, and then we have a 45-degree line. That's our constraint. Okay, so let me actually make sure we realize that line here. And now we are allowing points on that line because we have a equal line. It's a closed set of values, and values for x2 smaller than that line. So values which are below that line are allowed. So that's this blue shaded area. These are the values which are allowed. What about that second constraint here, this constraint? So it says that x1 should be smaller or equal to 2. So remember, that's the x1 axis here, and here we have 2. So the values which are allowed are all the values of x1 which are 2 or smaller. So it's that orange shaded line. So that constraint, of course, also goes beyond the boundaries of that particular picture. So the combination of these two constraints now means that our solution, we are looking for a solution actually in this red sort of area. Okay, it's that area here which we are looking for. So it's the overlap of the two constraints, the area where both of the constraints are met. This is where we are looking for solutions. So how are we going to do this formally now? So in this picture, all you can see is the constraints. You can't see the function yet. It's a cubic function. We could perhaps plot in some level curves, but that would just make the picture really quite difficult to look at and wouldn't really solve our issue. We have to solve this with a Lagrangian method. Let's see how we adjust the Lagrangian method to the presence of a second constraint. We're just formulating the Lagrangian. It starts out as normal. It's our function plus the constraint, a constraint g, times the Lagrangian multiplier lambda. And since we have two constraints, we will have two Lagrangian multipliers, so I call one lambda g for the first constraint, and now the second constraint will just result in another Lagrangian multiplier times the constraint function itself. So this will be our Lagrangian function. We've added a second constraint, and perhaps you can already realize if you had a third constraint, you will just add a third term here. Now, we haven't really formulated our constraints yet, g and h. We have these two constraints, but remember, what we need is we need a constraint g of x1, x2, and some function of x1 and x2, which is larger or equal to 0. So how will we reformulate our constraint here is we're going to bring the x2 to the other side, and then we have negative 0.4 plus x1 minus x2. So this is the constraint we are working with. And what about that second constraint? We shall call that h, function of potentially x1 and x2. And again, we need that to be larger or equal to 0, so we'll just bring the x1 over to the other side, 2 minus x1. You realize that constraint is actually not a function of x2, and we could see that by looking at the graph, because that was just a vertical line here. So what we now need, as you know, the core of the Lagrangian method are the necessary Lagrangian conditions. So the conditions which any solution to the problem, i.e. any point with x1 and x2 coordinates, which we hope to be the maximum, which we hope to will deliver the maximum of our function, any such point needs to meet all of these conditions. Now usually when we have one constraint only and two input arguments, we are having four constraints. We're having the Lagrangian, the partial derivative with respect to x1, the partial derivative of the Lagrangian with respect to x2. We're basically just repeating the constraint. The constraint has to be larger or equal to 0, and we would have a complementary slackness condition here, which tells us that the Lagrangian multiplier has to be larger than 0, and that the product of the multiplier times the constraint function has to be 0 at the solution. Now that we are having a second constraint, we're adding two conditions. Firstly, just the second constraint. It has to be larger or equal to 0. And we're adding a second complementary slackness condition. The Lagrangian multiplier to the second constraint also has to be larger or equal to 0. And we have a second complementary slackness condition. So our potential solutions now have to meet all of these 6 conditions. So what is the solution to the problem? Let's firstly, before we continue, find out what our partial derivatives of the Lagrangian with respect to x1 and x2 are. Okay, so we can basically, we will look at our function. Let me actually write down the Lagrangian here. So here we have the function, which is 4 times x1 cubed minus 6x1 squared minus 2x2 squared plus 2. Now plus lambda g times the first constraint minus 0.4 plus x1 minus x2, and then plus lambda h, I'll continue that here, plus lambda h times the second constraint, which is just 2 minus x1. So now we can write down the partial derivatives with respect to x1. That will be 12x1 squared minus 12x1, and then the next x1 is over here in the first constraint, so it's x1 and multiplied with lambda g, so it's plus lambda g. And then in the second constraint we have negative x1 multiplied with lambda h, so that will be negative lambda h. And that needs to be equal to 0. That's one of the Lagrangian conditions. So the second partial derivative, we get negative 4x2. And the only other x2 here is in the first constraint, negative x2, so that's multiplied with lambda g, so we have negative lambda g. So these are now our conditions. When we try and find the points which meet these conditions, we sort of separate out our area, allowed area, into certain areas. It's usually the unconstrained bit and then on the constraint. But now we have two constraints, so we have to think about this. So firstly, we will look at the unconstrained area. That is sort of the area in here, okay, between the two constraints. And in here, we will have to assume that lambda g is equal to 0 and lambda h is equal to 0. So that will be our unconstrained area. Then you know from the normal Lagrangian method, we will be looking at values on the boundary. So now we have two boundaries. So we will be looking for values on the boundary of our first constraint, so that these are these values here. And we'll basically look for values up until here, because afterwards they will not be allowed. So to look at this, we will have to look at the case where lambda g is larger than 0, but we will temporarily assume that lambda h is still equal to 0, so that second constraint isn't binding yet. And then we will be looking at the second boundary. Now we just, where's our second boundary here? It's orange. Let me make that a little thicker. We'll then be looking at this boundary here and see whether we can find potential solutions here. Sorry, that boundary has become a little bit thick. Okay, and so this is where we'll have lambda g equals to 0, but lambda h, so let me just write that here, we'll get there. So lambda g will be equal to 0, but lambda h will be larger than 0. So as it turns out, if we will not have found a solution here, what we will also need to look at is this sort of intersection point. Okay, that's where both constraints are binding, but we will only have to look there if we haven't found any potential solution on the boundary, on the blue bit and the orange bit. So let's start and look for unconstrained potential solutions. So that's fairly straightforward. We set both of the lambdas equal to 0, so we end up with 12 x1 squared minus 12 x1 is equal to 0, and the second condition, minus 4 x2 is equal to 0. So you can immediately see that x2, we learn from here that x2 has to be equal to 0. What about x1? Well, from x1, we're working from this condition here. Let's factor out to make that it's a quadratic equation x1, so we can have potentially up to two solutions. So let me just continue up here. Well, I'm going to factor out 12x1. That will make it easiest. So we get 12x1 is equal to x1 minus 1, and that is equal to 0. So from here you can see that they're where the two solutions are. The first one from here is that x1 is equal to 0. That will make this entire term 0, and we have a solution to this equation. The second one comes from here. If that second term goes to 0, then we also have a solution, and that will happen if x1 is equal to 1. Okay, and both of these points are of course paired up with the x2 value, which we know to be 0. I'm not sure why I wrote the a. Well, I was anticipating what I wanted to write. And here we also have x2 equals 0. So we're having 2 points. Let's call these points A and B. And let's go to our diagram and see where are these 2 points. Well, A is on the origin. That's this point here. Okay, that's point A. And you can see that this point isn't in our allowed area because it breaches the G constraint. All right. Just remember that blue line, that was the G constraint, and the orange line here, that was the H constraint. So we're breaching that. You can test this formally by plugging in 0, 0 for x1, x2 into the G function up here. And then you get -4 plus 0 minus 0 is -4, and that is not larger or equal to 0. So that means this point A is not a candidate solution. It doesn't meet all of our Lagrangian conditions. What about point B? So let's draw it first. x1 equals 1, x2 is 0. That is around here. It's halfway between the origin and the constraint, which is at 2. So this is point B. So here we still have a potential solution. It's in the area which is allowed, and you could plug 1 and 0 into both constraint functions, and you could confirm that they are both larger than 0. So, well, we're continuing to work with this value. We're not dismissing it. Let's find out what the value, the function value at that point is, f1, 0. And if you plug this into the original function, you will find that the function value here is 0. Okay, just confirm it. I will, at several stages in this question, just jump over the algebra a bit where I think that the algebra is straightforward enough from there. So we have looked for unconstrained potential stationary points. We found 2, A and B, but only one of them was allowed by the constraints, by the 2 constraints. So far we found one potential solution, one point B, which hits all of these 6 values. Remember, we assumed lambda G and lambda H equal to 0, so that's why these last 2 were met by assumption here. So let's start looking at the blue boundary. So this is where we said that lambda G is larger than 0 and lambda H is still equal to 0. So we're not constraining our, we're not using the H constraint. We're only looking at the G boundary. So let's write down our Lagrangian conditions under this condition. So we're having 12x1 squared minus 12x plus lambda G is equal to 0. And we're having minus 4x2 minus lambda G is equal to 0. So we're having 2 equations so far with 3 unknowns, x1, x2, and lambda G. Sorry, that was an x1 here. And lambda G. So we need a third equation. That's where we use the complementary slackness condition here. Because if lambda G, if this value here is larger than 0, then the G function has to be equal to 0 for the product of the 2 to be equal to 0. So that means we go to our G function and just use the 0, and that will give us the third equation, negative 0.4 plus x1 minus x2 is equal to 0. So here we have this so we need to solve this. We have 3 equations, 3 unknowns. We can potentially solve this. So how are we going to do this? I'll skip over lots of the algebra here. We'll start out by solving the first equation for lambda G. So lambda G is equal to something. And the second equation for lambda G, and so we get lambda G is equal to something, and then we can set these 2 parts equal to each other. When you do that, what you get is negative 12x1 squared plus 12x1 is equal to negative 4x2. Okay, so that's what you get. So you have an equation in x1 and x2. We want to get rid of, for instance, the x2, so we get an equation in one variable only. We can get that from this third equation here, because this one here solves to x2 is equal to, we are just bringing the x2 to the other side, negative 0.4 plus x1. So we can use this and plug it into this equation here. Actually, before we do that, we'll actually simplify that. We'll divide this by negative 4, just to make it look a little easier. We then get 3x1 squared minus, because I divided by minus 4, minus 3x1 is equal to x2. And now we use what we found here. So you get 3x1 squared minus 3x1 is equal to negative 0.4 plus x1. We'll bring everything onto one side. So we get x1 squared minus 4x1 plus 0.4 is equal to 0. So this is just a quadratic equation which you can solve with your favorite quadratic formula. Now let me just draw a line under this. So I'll leave you to do that. We get the quadratic equation, we get two potential values, and let me just tell you what these values are. And I call these points are two potential candidates, C and B, with two different x1 values. So one of these values will be 1.2244, and the other one will be, let me get that right here, 0.1089. So, okay, that's just an application to solving this quadratic equation. Now, once we have x1, we also have x2, because remember here, x2 is just x1 minus 0.4. So let's write down what that is. So x2 here is going to be 0.8244, and here it's going to be negative 0.2911. Okay, now we also need to know what the lambda g is. The lambda g, actually I'll temporarily give myself a bit more space here. We'll get back to that point. So what the lambda g is, now once we have x2, we know, actually I should write that down, from this equation here, when we solved for lambda g, what we actually did get here is that lambda g is equal to negative 4x2. So once we know x2, we know what lambda g is, and that is a negative, I calculate what it is, yeah, negative 3.3, and here the lambda g is equal to 1.1644. So here you can see we have a negative value that is smaller than 0. That means that this point does not meet our Lagrangian conditions, because what we need is that lambda g is larger or equal to 0. How does that, how come? Well, remember what we did is, no, okay, I'll just leave it like this. So before we can do, next what we need to check, of course, is whether this solution here, D, so we dismissed point C as the solution. What about D? Are we sure this is the solution? Well, not quite yet, because we haven't checked whether this point at point D, we are conforming to the second constraint, the H constraint. Okay, we were looking on the G constraint and we found a particular point. So let's see where in the graph that point is. The point is 0.1 and negative 0.2. So it is somewhere here. It's this point here. That point here is D. Now clearly it's inside the H constraint, and of course you can plug in H1 into the H constraint and you can find out that it is still larger than 0. So that's all good. So this point is a candidate solution. Let's find out what the function value at that point is. The function value at point D, so let me not repeat the coordinates, I'll do it like this, at point D. So you can plug all of these values into the function, and when you do that, what you get is 1.7645. So where are we at? And let me also draw in where C is. Okay, C is 1.2 x2 is somewhere here. Okay, that was the C point. Okay, so we identified so far, looking on the red area inside and on that blue branch of the constraint, we looked for potential stationarity points. We sort of temporarily found 4, A, B, C, and D, but eventually we decided that neither A nor C are actual candidate solutions. Okay, only D and B survive. Between D and B, we can compare the function values, and we can see that actually at D we have a higher function value. So here on the boundary is a higher function value than at B. So in some sense we now have only D to work with. But let's now continue looking, and now we look on the orange branch here. Okay, so that is where lambda H is larger than 0, but lambda G we temporarily set equal to 0. Okay, we're looking on the orange branch. So let's go back to our Lagrangian conditions. What do we get here? We get 12 x1 squared minus 12x1 minus lambda H is equal to 0. And then we also get minus 4x2. There's no lambda H in the second condition, so that's just minus 4x2 is equal to 0, and lambda G is set to 0. So 2 equations, 3 unknowns, x1, x2, and lambda H. We need a third equation. We're going to this complementary slackness condition. If we set lambda H to be larger than 0, then H has to be equal to 0. We go to H. Our constraint is 2 minus x1 is equal to 0. So this solves very easily, because as you can see, we get from here that x1 has to be equal to 2. That is not a surprise, because we said we are looking on the orange boundary, and everywhere on this boundary x1 is equal to 2. What about x2? Well, from this here we get that x2 has to be equal to 0. So we have our point, let's call it point E. That is at x1 is equal to 2, x2 is equal to 0. What about lambda H? Okay, so we can see from here that lambda H, from this equation, that lambda H is equal to 12x1 squared minus 12x1. So what do we get here? Okay, we're basically getting lambda H is equal to, so lambda H is equal to 12 times 2 squared minus 12 times 2. 12 times 2. So 2 squared, that's 12, that's 36. Okay, so you get 36, the lambda H of 36. This is larger than 0. of course, as it should be. Is it actually 36? Hang on. We have 4. No, sorry, it's 24. There you go. Too quick. So it's 24, and that is larger than 0. So far that point meets the constraint H, and therefore all the Lagrangian conditions, but what we haven't checked yet is how it stacks up against constraint G. So let's draw in our point in our diagram. It's a 2, 0. It's this point. Okay, that is point E. And you can perhaps see it does seem to meet our constraint, our G constraint, but you could confirm that by plugging in the coordinates 2, 0 into the G constraint. So -4 plus 2 is negative 1.6 minus 0 is 1.6, which is larger than 0. So that point is okay. And now let's see what the function value at 2, 0 is. Well, if you plug in 2 and 0 into the function, what you will get is 10, a function value of 10. So what you now remember, what we earlier found out, we found out that D has a higher function value than B, and now we found out that E has a higher function value even than as D. Okay, because D had a function value of 1.76, and now we have a function value of 10 at that point E. So our remaining possible solution is E. So what we now need to figure out is we have one possible solution. We found one point that meets all, no, actually we found 3 points that meet all the necessary conditions, and we identified which of these 3 points has the highest function value. That's point E. What we now need to figure out whether that's really the solution to the problem, or in other words, whether we have like a global solution to the problem here. Firstly, the constraints are not compact. Okay, so you can see we have in linear constraints. These constraints are not compact, so we are not guaranteed a solution here. Are the constraints concave and the function concave? Because if the answer to that question is yes, then we know that the Lagrangian conditions would not only be necessary but also sufficient. So let's look at the constraints. The constraints are linear constraints, and we know that linear constraints are concave. They're also convex. Linear constraints are both concave and convex. They're both concave. But what about the function here? Now we're having a cubic function. Those of you experienced will realize that if you have a cubic function as the dominant power here, that's the highest power, x1 cubed, such a function isn't going to be concave. It has concave and convex parts. So this one is not concave. Okay, you can of course confirm that if you calculate the Hessian for this function and see whether that is negative semi-definite everywhere. If it was so, the function would be concave. You'll find out that it isn't, but you can already see that here. So our Lagrangian conditions remain only necessary conditions. So this is where we have to go back to our diagram here and have to figure out how the function behaves in the allowed area. So that's in this red area. And you can see here it's actually a very restricted function. But what we need to watch out for here is what happens, because what happens as x2 goes to negative infinity. Because that can happen. Okay, the function is allowed to develop into this area. So what we need to figure out here to establish that is we need to look at the partial function, and we look at the partial function where let's set x1 equal to 0. So we're looking on that axis, and then we are looking at x2. And we are interested in what is the limit of that function as x2 goes to negative infinity. We are not interested in the limit as this function or as x2 goes to positive infinity, because that's not an allowed area of the function. We're only interested in the allowed area here. So let's write down the partial function. That simplifies quite a lot. That is just negative 2x2 squared plus 2. So what happens to this function? Oh, apologies, I should not forget the limit. So we're interested in the limit as x2 goes to negative infinity of negative 2x2 squared plus 2. Okay, and that, if we find out what the limit here is, we understand how the function behaves as we go down here. So we have x2 squared. If x2 goes to negative infinity, x2 squared goes to positive infinity. But then we are multiplying that with negative 2. So that term goes to negative infinity plus 2. Doesn't change anything really. So this is the limit of that partial function as x2 goes to negative infinity is negative infinity. So that means as the function moves into this direction, there is no threat to our current maximum value at e. And since this function can't really develop into any other direction where it could sort of increase a lot over that value, we have found that point E is the solution to the problem. Okay, at point E we are maximizing that function conditional on these two constraints. So hopefully you can see, let's slightly recap what we've done here. The trick here was really in understanding how to adjust the Lagrangian method for a second constraint, and hopefully you can see how you would do it for even more than two constraints. We're adding conditions to our set of Lagrangian conditions. In fact, we added this one here and this complementary slackness condition, and in some sense from then onwards everything works in the same way. We're looking for points which meet all of these 6 conditions. It's just that now we're sort of looking in sort of more areas. We're looking inside, that was the red area, then we are looking at this branch, that blue branch of the constraint, and then at the orange branch of the constraint. Now I said at the beginning, what about this point here, the purple point? I almost forgot about that. Why don't we have to check out this one? Well, if that point here, that purple point, was better than point E, we should have found it, and if it had met all the stationarity conditions, all the Lagrangian conditions, then we would have found it as we worked here. But we found another point. So here we found a point. Okay, and as it turns out, this point will dominate this point. If we thought, because what we did for starters is that we looked everywhere on that boundary, and only once we found point E, we then checked whether that point E hit the other condition. So we actually did look at the entire line, and then subsequently decided whether the point we found met that G condition, and therefore restricted us to that bold orange part. Okay, so if that purple point was a better point than E, and a point that also met all of the stationarity conditions, we would have found it here. Conditional, we found a point here. Okay, if we found another point, then we know it's not that purple point. There's one case where you may have to look at that point, and that is if you don't find a possible solution here and don't find a possible solution here, then you would also have to look for lambda h larger than 0 and lambda g larger than 0. And then you would just get these two conditions with both lambda g and lambda h. So you would have 4 unknowns, x1, x2, lambda g, lambda h. And then you would have to enlist both of these constraints, both of these equations with the equal part. And then you would have 4 equations for 4 unknowns, and you could solve that, potentially, if there is a solution. Okay, I hope you understand, or that helps you to see how we adjust the Lagrangian method to deal with higher dimensional problems, higher dimensional here in the context of having more than one constraint.